Hi, I'm Alex, and welcome to Super Make Something, the show where I make something cool and show you how to make it too. Today, we're building a 3D printed replica of the arc reactor from the movie Iron Man. Let's get started. The arc reactor is made out of the following components: one ATtiny85 microcontroller, one coin cell battery holder, one single pole dual throw mini power switch, one 10 kiloohm potentiometer, one NPN transistor, one 10 kiloohm resistor, one custom interface PCB, 11 royal blue Adafruit sequin LEDs, one 3D printed diffusion ring printed out of clear PLA, one circular piece of wire mesh, 4 3D printed concentric rings, one 3D printed center ring assembly, 10 3D printed coil spacers, 30 gauge copper magnet wire, 40 silver solder pads cut out of cardstock, jumper wires to bridge the coil spacers, one 3D printed base plate, and 5 M2 screws to hold the circuit board and center ring assembly in place. I began this build by searching for the arc reactor's dimensions online. The general consensus on the replica prop forum was that the outer diameter of the diffusion ring was 3 inches. Based on this, I next headed to Google Images, where I found a front view image of the officially licensed Iron Man movie arc reactor prop replica. I saved this image, opened it up in Inkscape, and then scaled it so that the outer diameter of the diffusion ring matched the diameter that I found online. This allowed me to extract the rest of the dimensions for all other features on the arc reactor by tracing lines on the photo and writing down their lengths. This process took a while. To give back to the online prop making community, I decided to make a dimension drawing from these measurements, which will hopefully save someone some time should they decide that they want to make this arc reactor using a different method than 3D printing in the future. In case you're interested in taking a look, a link to the drawing can be found in the video description below. Once I had extracted all of the dimensions from the arc reactor photo, I opened up SolidWorks, a computer-aided design or CAD software package. Here, I created 3D models of each of the arc reactor pieces in the photo using the line lengths I had measured in the previous step. While the photo allowed me to get the length and width of each component, it did not provide any depth information. This gave me some freedom to model these dimensions to best fit my design idea. Specifically, I decided to emphasize wearability. I wanted to make sure that the height of each piece was as short as possible in order to make the arc reactor as thin as possible. My thinking here was that this would make it easier to wear this prop for an extended period of time and minimize the risk of accidentally bumping it into things and breaking off components. During this process, I simultaneously created a virtual assembly of the arc reactor, which allowed me to make sure that all of the pieces would fit together, as well as add features and modify dimensions on the fly. Once I was satisfied with the overall look, I saved each component as an STL or stereolithography file, which generates a mesh of each piece that can then be 3D printed. Next, I opened up Cura, a free 3D printing slicing application in order to generate G-code to tell my printer how to make each object one layer at a time. Because this arc reactor has a lot of fine details, I printed each piece at 0.1mm layer height. I also decided to print the diffusion ring with 100% infill to avoid having a grid pattern shine through the translucent plastic when it is lit by the LEDs. Finally, I also enabled supports for each piece, since the arc reactor has many components with overhang features which allow the pieces to nest together vertically. Once everything was set, I exported the G-code to an SD card and plugged it into my 3D printer. Overall, the arc reactor is surprisingly small, with the biggest piece being the chest harness that all of the other components mount to. Because of this, all of the pieces should be able to be printed without splitting them up any further on most hobby printers. I'm printing my pieces on the Monoprice Mini Delta, which has a circular build area with a diameter of 110mm or roughly 4 1/3 inches. While this is small compared to some other printers available today, it was more than enough space for each of the arc reactor components. Delta printers have the advantage of being able to print slightly faster than printers that use an XY carriage, however these shots are time lapses, not real time. The total print time for all components was approximately 10 hours. While the components printed, I headed back to my computer to start on the project's electronics. Since one of my design goals was to make the arc reactor as short and self-contained as possible, I decided to create a custom circuit board to light and power the device. I first headed back to SolidWorks and opened up a CAD model of the PCB or printed circuit board that I modeled in the previous step. Because the electronics need to stack behind the 3D printed components of the arc reactor, the circuit board needs to have a custom circular shape that needs to be specified during the PCB design process. To do this, I saved the circuit board outline as a DXF or drawing exchange format file, which I could import into my PCB software when laying out the board in the next step. The circuit board was designed in Eagle, a schematic and PCB layout program available from Autodesk. Once the program loaded, I started a new project and then created a new board. I next imported the DXF file from the previous step using Eagle's DFX import function found under File, Import, DXF. After locating my file using the Browse option and making sure that the Target Layer dropdown option was set to 20 dimension, I clicked OK and then clicked the Run button in the following window. This imported my board outline into Eagle, though not all of the pockets in the drawing were recognized as closed contours. To fix this, I found the open line in each of the pockets and set their X and Y locations to be coincident, which changed the pocket color to gray, indicating that it will be milled out during the PCB fabrication process. I next clicked on the Switch to Schematic button located in the Eagle taskbar, which took me to a new screen that would allow me to wire up the arc reactor circuit. While the details of using Eagle are outside of the scope of this video, the PCB design process essentially boils down to placing the components you would like to use into a schematic and connecting them together appropriately using virtual wires. Once the components were wired up in the schematic, it was time to arrange the arc reactor's electronic components on the circuit board. Clicking the Generate/Switch to Board button at the top of the Eagle taskbar switched back to the board layout graphical user interface, where components from the schematic could be moved around to fit onto the PCB. Here, I first drew polygons that matched the size of the sequin LEDs that I would be using to light the arc reactor onto the circuit board for reference. This would help me place the SMD parts in the correct locations of the board so that I could solder them onto the PCB. I next began to populate my board, placing all of the SMD components on one side of the circuit board and all of the other components on the opposite side. Once the components were arranged to my liking, I used the Auto Route button to generate the PCB traces that connect everything together. Because you should never blindly trust the auto router, I next used the Show tool to inspect that everything was connected the way I thought it should be. I next added text and logos that will be printed on the circuit board's silkscreen layer to be able to identify the PCB. The final step was to make sure that the PCB followed the design rules of the fabrication house that I would use to manufacture the boards, which was done by clicking on the Check DRC button. After verifying that everything was good, I saved the board and closed Eagle. I manufactured the boards using Osh Park, a PCB manufacturer located in Lake Oswego, Oregon. On the Osh Park homepage, I simply uploaded the board file, waited for the board to finish processing, entered some information about the PCB on the following page, verified that everything looked okay one final time on the confirmation page, and then clicked the purchase button. 3 weeks later, I received 3 copies of my board in the mail in an awesome purple color. The video description below contains both a link to the Gerber files, which you can use to fabricate your own copies of the board at your favorite fab house, as well as a link to a website where you can buy individual copies of the board directly. With the PCB in hand, it was time to program and assemble the arc reactor's electronics. The core electrical components of this project are an ATtiny85 microcontroller and 11 royal blue sequin LEDs from Adafruit. In addition to these components, this project also uses one coin cell battery, one coin cell battery holder, one 2N2222 NPN transistor, one single pole dual throw on-off switch, one 10 kiloohm potentiometer, one 10 kiloohm resistor, and one 6-pin DIP IC socket adapter. This last component is completely optional, but will allow me to remove the ATtiny from the circuit board once everything is assembled in order to program new light patterns without desoldering the chip. Before continuing, let's take a look at the circuit behind the arc reactor. The ATtiny85 microcontroller essentially acts as a bare-bones Arduino, without any supporting hardware like USB ports, voltage regulators, and other components found on bigger, commercial versions of these boards. Power is supplied to the ATtiny using a 3-volt coin cell watch battery, which also powers the rest of the electronic components in the circuit. A potentiometer is connected to one of the microcontroller's analog read pins, whose resistance can be adjusted to change the voltage across the microcontroller's sensing pin. This voltage is then read by the ATtiny, which uses this value to generate a PWM command that changes the brightness of 11 parallel surface mount LEDs, each of which has a corresponding in-series resistor. Unfortunately, the LEDs cannot be powered from the ATtiny's PWM pin directly because they would draw more current than the pin can supply. Therefore, the positive terminals or anodes of the LEDs are directly connected to the 3-volt line of the battery, and an NPN transistor is located between the LED resistor pair's negative terminal and the rest of the circuit's ground line. Unlike the Arduino pin, transistors can handle large currents across their emitter and collector pins, opening and closing the circuit based on relatively low input current at their base pin. This essentially makes transistors a type of electronic switch. The transistor's base pin is connected to the ATtiny's PWM pin through an in-series 10 kiloohm current limiting resistor, and opens and closes the connection between the LEDs and ground depending on whether the value of the PWM signal generated by the ATtiny is low or high. By quickly flashing the LEDs on and off using this PWM signal, the LEDs appear to be lit at different brightnesses depending on the length of time the PWM signal is high versus the length of time the PWM signal is low. This is also known as the PWM duty cycle. Finally, a power switch is located between the battery's positive voltage terminal and the rest of the circuit, which can be used to turn everything on and off. The ATtiny 85 is programmed using the Tiny AVR programmer from SparkFun. While it is necessary to install a driver and board definitions to use these components with the Arduino IDE, the installation process is incredibly straightforward. Tutorial links about how to do this can be found in the video description below. Once everything was set up, I plugged the Tiny AVR programmer into my USB port and started the Arduino IDE. The code for this project is also very straightforward and does the following. The code first declares variables that define the pins that will be used to output PWM signals and read the potentiometer, as well as a variable for the PWM value. It next sets the PWM pin as an output pin in the setup method. In the main method, the program first performs an analog read of the potentiometer value. It next maps this value between the range of 0 to 255, which, for the Arduino, correspond to a signal that is either entirely off or entirely on. Finally, it outputs this value on the PWM pin, pauses for 100 milliseconds, and then loops again. Once I was happy with the code, I ensured that the following options were selected in the Tools menu. Board option ATtiny 25, 45, 85, processor ATtiny 85, and clock internal 1 MHz. I then clicked the Upload button, which compiled the code and uploaded it to the microcontroller. Once the LEDs on the Tiny AVR programmer stopped blinking, I unplugged it from the USB port and could begin to solder all of the components to the PCB. I began by mounting my circuit board into my PCB holder. I next soldered all through-hole components, beginning with the potentiometer, followed by the 6-pin socket adapter, 10 kilo-ohm resistor, on-off switch, transistor, and battery holder to the circuit board. After inserting the watch battery and turning on the power, I flipped the PCB over and applied a drop of solder to matching solder pads. I then held the LEDs in place and remelted the solder on the pads, which electrically connected the LEDs to the rest of the board. Since the power was on during soldering, the LEDs lit up to indicate that the electrical connection was good and that everything was soldered correctly. I then repeated this for the remaining 10 LEDs. Once the electronics were done, it was time to paint the arc reactor. The 3D printer made the following components: 1 base plate, 1 diffusion ring printed out of clear PLA, 10 coil spacers, 1 3D printed center ring assembly, and 4 concentric rings. The arc reactor components were painted using black, gunmetal, silver, and gold acrylic paints that I bought from my local craft store. I first added drops of each of these colors into a 6-well plastic palette, which would allow me to mix the paints together without making a mess on my cutting mat. Because some of the components were also very small, but needed to be painted evenly from every side, I used a sheet of paper as a backdrop and applied pieces of double-sided tape to its middle. This allowed me to tape my pieces to the paper and keep them from moving around while painting. I began by painting the 4 concentric rings using gold paint. I wanted to go for a worn look, so I did not worry too much about painting all of the pieces evenly. Instead, my strategy was first to paint everything using a bit too much paint, dry off the paintbrush, and then go back and spread the paint to make sure that everything was covered. The center ring assembly was painted with a mix of black and gunmetal paint, with a final dry brush layer of black paint to enhance some of the piece's details. The coil spacers were painted with silver paint, which I left attached to the 3D printed support material to keep everything upright and make painting easier. While the painted pieces dried, I began to assemble the arc reactor. I first inserted the PCB into the diffusion ring. I then attached these components to each other using 3 5mm long M2 screws, making sure that the circuit board was oriented so that each of the LEDs were located underneath the diffusion ring's indentations. I next inserted the 10 coil spacers into the indentations, gluing everything together with a dab of superglue. Once this was complete, it was time to wrap the coils using 30 all-wire gauge enamel-coated magnet wire. I first cut an arm's length of magnet wire from the spool. I then inserted one end of the wire into a slot in the diffusion ring, wrapped a piece around the neighboring slot to keep everything taut, and then wound the wire over the coils, through the slots of the diffusion ring and PCB, until the entire width of the coil was covered in a layer of wire. Once complete, I wound the start of the coil to the end of the coil to hold everything in place, finally cutting off any remaining wire using a pair of snips. I repeated this process 10 times, once for each coil spacer, which took a total of about 4 hours. The mesh portion in the arc reactor center is made out of an adhesive-backed screen door repair sheet that I picked up from my local hardware store. I first cut a 2x2 inch piece from the sheet using a ruler and X-Acto knife. I next traced the outline of the middle concentric ring onto the screen's backing sheet using a pencil, and cut out the resulting circle using a pair of scissors. I then peeled the screen off of the backing sheet, stuck it to the middle of the arc reactor, and used a hairdryer to melt the screen's adhesive to the diffusion ring. Once the screen was attached to the diffusion ring, I trimmed any excess with an X-Acto knife. I next pressed the smallest concentric ring into the channel in the diffusion ring. I then attached the other concentric rings to the 3D printed steps of the diffusion ring using dabs of superglue, positioning everything with a pair of tweezers. Once all the rings were glued, I placed the center ring assembly onto the top step and screwed it to the diffusion ring using two 10mm long M2 screws. The next step was to cut 40 3x2mm solder pads out of silver cardstock that I had bought from my local craft store. For this, I used my craft cutter, though this could also be done by very carefully cutting the cardstock using an X-Acto knife. After loading the cardstock into the cutter, the machine's knife moved through the paper cutting tiny silver rectangles. Because of the tiny squares and cut settings, I knew that some of the rectangles would slip off of the adhesive-backed cutting mat during the cutting process, potentially becoming unusable. To solve this, I simply cut more squares than I needed to, banking on the fact that I would get at least 40 good cardboard solder pads after the machine was done. Once it finished cutting, I ejected the mat and cardstock from the craft cutter, and then carefully picked off individual squares with my tweezers, putting them into a small bowl for safekeeping. The pads were glued onto the top and bottom front face edges of the coil spacers, again using superglue and tweezers. This step is entirely cosmetic, but really helps to enhance the arc reactor's likeness to the one worn by Tony Stark in the movie. The final step was to cut jumpers to bridge each of the solder pads out of gold craft wire. Instead of individually measuring each piece, I found it easiest to cut a small length of wire and then trim it to length to fit appropriately. The jumpers were again positioned using tweezers and attached to the pads using superglue. At this point, the prop portion of the arc reactor was done, so it was now time to make a harness using the 3D printed base, 1-inch wide nylon strapping, and 2 sets of parachute buckles. I first cut 2 nylon straps so that their combined lengths could wrap across my chest diagonally. I then melted the cut ends of the straps with a lighter to make sure that they would not fray. Next, I looped one end of the strap through the parachute buckle's male end so that I could tighten the strap by pulling on it. After this, I folded the end of the strap over to create a tab and then sewed it to itself. I then looped an end of the other strap through the buckle's female end and sewed it to itself into a loop. After this, I inserted a free end of one of the straps into one of the slots of the chest harness, doubled it over, and sewed it into a loop. I then inserted the remaining strap's free end into the slot diagonally across from the first slot and repeated the process. I then did all of these steps again for the second set of parachute buckles. I next adjusted the brightness of the LEDs using the potentiometer, screwed the prop portion of the arc reactor into the base plate, and the arc reactor was done. The final step was to strap the arc reactor to myself across my chest, put on a black t-shirt with a hole cut into it, and put on an Iron Man themed hoodie to complete the look. I now had a 3D printed, dimmable, and completely self-contained arc reactor that I could wear to midnight premieres of Marvel movies, use as a quick Halloween costume, or to simply have an interesting movie prop that I could display on my desk. The arc reactor is a fun weekend project for anyone looking to have their own Iron Man movie prop. In case you would like to build this project yourself, the video description below contains links to STL files for the arc reactor's 3D printed parts, a link to the ATtiny85 code, a complete bill of materials for the project's electronic components, a list of tools that I used during my build, and a link to the circuit board's design files that you can get manufactured at your favorite fab house. In case you don't want to deal with PCB design files, the video description below also contains a link to an online store where you can order the bare PCB directly. As always, if you end up making this project yourself, I'd love to see it. Please share pictures of your arc reactor or other cool projects with me using the social media links in the video description. In the meantime, thanks again for watching. Now go super make something. Thanks for watching! If you enjoyed this video, please be sure to hit the like button and share it with your friends. Your support helps me make more episodes. Links to all project files can be found in the video description below. Click the subscribe button on the left to keep up with my latest projects, click the cards on the right to check out more episodes, and connect with me on social media. Thanks again for watching, now go super make something!